Okay, welcome to part 2 of Waves Revision. If you remember, we did a little experiment where we shone a beam of light into a semicircular glass block. We shone it to the centre of the block, so it entered along the normal, so it didn't bend as it entered the glass block. But obviously, as it left the glass block, light going from glass to air bends away from the normal. You'll have noticed there's a little bit of reflection at this surface as well. Okay, but at this stage, most of the light goes through. And what we did is we made the angle of incidence bigger and bigger and bigger. Now, you may have noticed as the angle got bigger that the light started to disperse. We'll talk about that in a moment. But there is an angle where light no longer comes out the glass, where the angle of refraction is 90 degrees. The angle that this happens is called the critical angle. So the critical angle of incidence is when the angle of refraction is 90 degrees. Now, the angle is bigger than the critical angle, the light gets trapped inside the glass, and we call this phenomenon total internal reflection. And we're going to talk about some uses of that in a moment. Okay, so the critical angle is the angle at which the angle of incidence at which the angle of refraction is 90 degrees. At the critical angle bigger, the light stays trapped inside the glass, and we call this total internal reflection. Okay, we use this in right-angle prisms. So if you shine a beam of light into a prism, notice it's entering along the normal. Yeah, so there's no bending here. But when it's here, this angle here, the critical angle for glass is about 43 degrees, I think. This is 45 degrees, so the light stays inside the prism. This is an example of total internal reflection. The surface of the water here, the light is striking the surface at an angle greater than the angle of incidence, so it behaves as if it was a mirror. Okay, this is just a glass block here. The laser beam is entering along here. It enters at 90 degrees, so it doesn't bend. Hits the back surface. An angle of incidence that's bigger than the critical angle. Okay, it stays trapped inside. Same happens here. Same happens here. Same happens here. And it finally comes out of the glass because it's going along the normal. So it will just leave the glass. This is where we use the right-angled prisms. They're used in periscopes. They're much more reliable than ordinary mirrors. They stay clean and what have you. I've often tried to set this demonstration up in the lab. It never looks quite as good as this picture. But again, you can see this laser beam hits the surface of the water at an angle that's bigger than the critical angle, so it stays trapped inside. It's really hard to get this to look as good as this in the lab. I think maybe you need a darkened lab or whatever. And we use these in optical fibres. So an optical fibre really is just a thin piece of glass, and the light stays trapped inside because it hits the side of glass at an angle bigger than the critical angle. Now, these can be used for pretty lamps like this, but this is also how the internet is taken around the world. There are undersea cables where these fibre optic cables go under the ocean from country to country. They carry light signals, which carries the internet signals. So the internet is not carried by electrical wires, or not mostly. Electricity in metal wires, it's carried by light in these fibre optic cables. And we can also use these for endoscopes as well. So the light can both travel down them and be reflected. So you can put it down somebody's throat or up their bum, in this case here, and see what's going on inside. Okay, now there is a mathematical relationship between the critical angle and the refractive index of the glass, and that's the sine of the critical angle is 1 divided by the refractive index. And again, I might do a separate video to go through the mathematics of that, because I know we find using sines difficult. Okay, we then shone white light into a triangular prism, and we found that it was dispersed. Now, I've got this example. This is the famous album cover, Pink Floyd, Dark Side of the Moon. It's actually incorrect, this diagram. One, because the dispersion happens here. That this should be coloured light. And also you notice that the violet light here doesn't really bend, the white light doesn't bend here. So this happens because the different colours that make up white light, so our brain perceives white light, it's actually all the different colours arriving, our brain sees that as white. Violet light slows down more in glass than red light, so it bends more. So as soon as the white light enters the prism, it starts to speed up. Of course, when it leaves the prism, it speeds up. Red light has not slowed down so much. It won't speed up as much. It doesn't have to speed up as much. to get back to the original speed so it doesn't bend as much. Violet light has been slowed down a lot. It has to speed up to the speed of light in a vacuum. It speeds up a lot. It bends a lot. So this is what's happening inside. So you need to know this. You need to know the order. Red, orange, yellow, green, blue, indigo, violet. Red light is bent the least. Violet light is bent the most. If you remember copying that diagram down in the lesson. Okay, we're nearly there for waves. The Doppler effect. I didn't cue a video of this for this one, but you know when a car comes towards you, it sounds high-pitched. When it moves away, it sounds low-pitched. It happens with trains, all sorts of things. We looked at lots of videos of this in the class. So the Doppler effect is the apparent frequency of sound changes. So the sound from the car appears to be changing in frequency due to the relative movement of source and observer. So either the source, the thing making the sound, is moving, or the observer is moving. Now, there are different reasons for this happening. You don't really have to explain this, but I sort of did. Obviously, when a car is giving out sound, it's not moving. The sound moves out in spheres. The wavelength stays the same. When the car is moving towards the observer, it's actually catching up the sound waves that it's made. So the distance between the waves is less, i.e. has a smaller wavelength. If the wavelength is smaller, the frequency must be higher. Okay. If you do A-level or IB next year, you'll learn a formula to calculate the new frequency, given the old frequency, the speed of the source and the speed of the sound. You don't have to do this year. If the observer's moving, so if the observer is moving towards the sound, well, it appears to the observer then that the waves are moving faster. The observer's moving in this direction, the waves are moving in this direction. So to the observer, the waves appear to be moving faster. At the same wavelength, if the speed is bigger, that means the frequency must be bigger from the wave equation. Again, you don't have to explain that for IGCSE, but next year you will learn, next year in year 12, you will learn a formula to calculate the new frequency. Don't forget, of course, the loudness changes as well. So when the car's further away from you, it's going to be quieter. We use the Doppler effect in lots of things, but we can use it in sports to measure the speed of cricket balls or baseballs. We obviously the police use it to measure the speed of cars, and you can also use it to measure the speed of blood flowing around the body. Okay, the final part of waves is just going back to sound waves. Remember, sound are longitudinal waves. I won't go through this again. You should have learned this from the previous slide. Okay, where the particles and the sound wave are squashed together, we call that compression. Where they're stretched apart, a rarefaction. There is a connection between the amplitude of a sound and the loudness. So big amplitude means a loud sound, small amplitude means a quiet sound. Can you hear me? And there's a link between the pitch and the frequency. So high frequency sound sounds high, like a high note, like a flute would play or a violin, and low frequency is a low note, like the bass. Okay, there's a limit to how high human beings can hear. It's normally taken to be 20,000 hertz or 20 kilohertz. Basically, the skin in our eardrums can't vibrate faster than that. So we can't hear sounds higher than that. Other animals can, of course, so dogs have a higher range of hearing, so you can actually buy dog whistles that we can't hear but dogs can. We didn't do this, but if you want to make a string telephone at home, so you just need like a yogurt pot with some string tied to the bottom, the string has to be tight. So in this case, in this cartoon, this wouldn't work because the string is loose, but if you tighten the string, you can actually hear pretty well. And that's a good demonstration that sound can travel in solids. The sound is traveling on the stretched string. Sound travels very well in solids because the particles are close together, the vibrations transmit really easily. In fact, in steel, sound travels about 6,000 meters per second, 6 kilometers a second, incredibly fast. Sound travels pretty good in liquids and in water, again, because the particles are close together. So sound travels at about 1,500 meters per second, 1.5 kilometers per second in water. Sound actually doesn't travel very well in air or in gases. So the speed of sound in air is about 330 meters per second, which is obviously fast, but not quite as fast as in solids and liquids. And of course, sound cannot travel in a vacuum because there are no particles to vibrate. And finally, an echo is just a reflection of sound. Just be careful. There are questions where they give you the time it takes for the echo to return. Okay, give you the speed of sound and ask you to find how far away is the wall. And don't forget, the echo has gone from the man to the wall and back again. So in this case, the sound will have travelled 100 metres. So just be careful when you're doing calculations. Okay, I think that's it.